starting with quiz 1. First off, we're reacting a double bond with acid catalyzed hydration, which means we're going through our carbocation intermediate. Oh my. What's up with that? Doesn't sound good. Every time you're going through a carbocation intermediate, you should always consider a rearrangement. If a rearrangement is going to be more stable, that's going to lead to your major product. So with our hydration, we're adding a H and an OH across our double bond. So our hydrogen adds in the least substituted position because we get our more substituted carbocation. But this is a secondary carbocation, and we do have a hydrogen at this position, so we would expect a rearrangement to form a more stable tertiary carbocation, and that will lead to our major product. Anytime you go through a carbocation rearrangement, you must consider, anytime you go through a carbocation intermediate, you must consider a rearrangement that will lead to your major product. So that means that our alcohol adds on this carbon because of the rearrangement. Tertiary is more stable than secondary. This is not a isomer, a stereoisomer, because it's attached to two CH3 groups, but if it was, we would expect both enantiomers. But it's not, so we don't have to represent that. Now, if we look at the right reaction, we see we're reacting our Hg and our acetate, so our mercury acetate and water. Water is our nucleophile, so that means we're going to have an addition of OH, and followed by NaBH4. So that is going to be our demercuration reaction, where we're going to have our new oxygen carbon bond, and in this case it's going to be an alcohol. The advantage of this reaction is the mercury will not allow for a rearrangement, though we're still going to get a Markovnikov addition. So in this case, our more substituted position is carbon 2. So that's where we're going to get our addition of our alcohol is on carbon 2. And of course, our hydrogen would be on carbon 1. Now, in this particular case, the hydrogen comes from sodium boryl hydride. It's a source of H negative, and that replaces our mercury. The advantage of this reaction over our acid catalyzed hydration is that we do not have any rearrangements. Also, if this was reacted with instead of H2O, but an alcohol, then we would just get the addition of an OR bond instead of an OH bond. But in this case, we have water, so we add OH. Now, if we go down to the next reaction, if we look to the left, we're reacting with BH3THF followed by peroxide and sodium hydroxide. In this case, this is our anti-Markovnikov hydration, so we're still adding H and OH across our double bond, but we're going to have our OH to be anti. Now, in this case, the OH is coming from the peroxide, and this is not a radical mechanism. But we will get our syn addition because our boron and our hydrogen add at the same time across the double bond, and then our OH eventually replaces the boron. Also, our BH3, our boron, is going to add in the least substituted position because BH2 takes up more room than just hydrogen. Again, review those in your review of reactions. When I have those up, I have the intermediates that specify regiochemistry and stereochemistry. So our alcohol is added to carbon 1. Now, that means that carbon 2 is now a stereocenter. We're only forming one stereocenter, so we're going to get both enantiomers. If we were forming 2, we would only get the syn addition. We don't have to show the hydrogen to show that we have a stereocenter. We can show our CH3 group coming forward plus our enantiomer. But carbon 1 is not a stereocenter. If they are both stereocenters, this would add syn because the BH3, the boron, and the hydrogen add at the same time. If we look to the right, well, we don't have our reagents, but we see that we had an addition reaction because we don't have a pi bond any longer. So the question is, what did we add across the double bond? If we look at carbon 1 in our starting material, we have 2 hydrogens and nothing else. On carbon 1 in my final product, I have still 2 hydrogens and a bromine, a Br. So that means I added bromine. Now if I look at carbon 2, I had 0 hydrogens, and in my product, I have 1 hydrogen. So that means that I must have added a hydrogen on carbon 2. So I added a hydrogen and a bromine across my double bond. Notice my bromine added in the least substituted position, so that's my anti-mark. So if I added a hydrogen and a bromine, I must have used HBr. And to have it anti-Markovnikov, I have to use peroxide to go through that radical reaction, which we now know how to do because we learned about that in chapter 11. So that's how you should be looking at this. What was added across the pi bond that entails our reagent. If we look at C, we're adding H2 and palladium. So clearly, we only have hydrogen. We're adding hydrogen across the pi bond on each of the carbons. And remember, if this was a triple bond, it wouldn't stop at the double bond. But here we have a double bond. This is going to be syn addition because our metal is heterogeneous, meaning it doesn't dissolve. So whatever face our pi bond comes in to interact with the metal that has the hydrogens absorbed on it, that's the side our hydrogens are going to add. So this is syn. If one side interacts with the metal, that's the side the hydrogen is going to add on. The other side interacts with the metal, that's the side the hydrogen is going to add on. Both sides can interact equally, but we never get anti-addition. Both hydrogens add on the same side, whatever pi bond, whatever side connects with the metal. Because remember, the metal is not dissolved in solution. It is a solid catalyst. It is heterogeneous. So whatever side pi bond interacts with the metal first, that's the side both of the hydrogens add on. So we get syn addition of hydrogen and hydrogen. So we would typically get both enantiomers of our syn addition, but in this case we don't get another enantiomer because this is a meso compound. We have that mirror plane, so I can show both my CH3 groups coming forward or both of them going back, but I don't have an enantiomer. My enantiomer is equal to this compound. An enantiomer is a non-superimposable mirror image. This mirror image is superimposable. Because of that mirror plane, if one side was an ethyl and the other side was a methyl, we would get both enantiomers. But in this case, it's not true. Now looking at D, again, the reagents aren't being shown, so the question is, what are we adding across the pi bond? Because in our final product, we do not have a pi bond. So what we see is on carbon 1, in my product, I had 1 hydrogen in my starting material. Now I have an alcohol and a hydrogen in my product. So that means I added an alcohol on 1 carbon of the double bond. And then on carbon 2, I had no hydrogens and no alcohols in my starting material, and in my final product, I have an alcohol. So it means I added 2 alcohols across my pi bond. So this is my dihydroxylation. Now, we had 2 different main reagents that we talked about for dihydroxylation, and that was reagents to form anti-dihydroxylation or syn. So the question is, how were these alcohols added? If you see in the final product, our alcohols are on opposite sides of the ring, so this is anti-dihydroxylation. So we need to show that by our reagents. Our reagents to get our alcohols on opposite sides of the ring would be going through our epoxide intermediate. Because our epoxide intermediate blocks one face, the second alcohol has to attack on the opposite face, hence why we get anti. So to form our epoxide, we have to use RCO3H. So this is our peroxy acid. In the book, The specific peroxy acid the book likes to use is MCPBA. I would accept MCPBA. I would accept RCO3H. Then, that just gives us our epoxide. The second step, the second alcohol, is going to come in through our addition of H3O+. Our acid will make our OH a good leaving, will make our oxygen a good leaving group by protonating it, and then water can attack. But it has to attack anti. If it was the SEN dihydroxylation, we talked about using KMNO4, cold KMNO4 and sodium hydroxide. That would put our two alcohols on the same side, or our osmium tetraoxide. That would also put our alcohols on the same side, because that is the two alcohols added at the same time. It's a concerted reaction. In this case, it's anti because of the epoxide. All of our reagents that go through this three-membered ring intermediate are all anti-additions because that side is blocked. So that's Br2 goes through the bromonium. Our mercury as well, but usually with our mercury, because we get our least substituted hydrogen, our hydrogen adding in the least substituted position, we usually don't get to stereocenters, so we don't really talk about it as much. Now if we look at E, we reacted our O3 and DMS, so that means we did our ozonolysis. At this point, we had only talked about double bonds, where if we have our double bond and we react with ozonolysis, we're going to form our aldehydes and our ketones and fully break the sigma bond. Whereas all of our other addition reactions, we did not fully break the sigma bond. And depending on what's attached, we already had a hydrogen attached on each of those carbons. That's why we have a hydrogen in our final material. Now with a triple bond, we get two additions of oxygen because we have two pi bonds, so then we form carboxylic acids. But our final products here don't have carboxylic acids, so we know we're going through the double bond. So the question is, where are our two C-double bond O's? Because that's where our double bond had to have been. We had a bond between those two carbons. So if we look at our final product, we see that our double bond oxygen is on carbon 1 and carbon 5, so our double bond must have been on carbon 1 and carbon 5 because we fully broke that bond. So that means if carbon 1 and carbon 5 are attached, we had a 5-membered ring that we started with. So just drawing my 5-membered ring, 1, 2, 3, 4, 5. My double bond is between 1 and 5, so I'm going to draw that. And then I'm just going to draw everything else that's attached. On carbon 1, I have a hydrogen. That's true. I don't really have to draw that hydrogen in. On carbon 2, I have an ethyl group. So I'm just going to put an ethyl group on carbon 2. And then I have this 5-membered ring that's attached on carbon 4 and 5. So I'm just going to draw that because I didn't do anything with that. I should have the same number of carbons because all I did was open the ring. So numbering can really help you with these. And of course, this does agree with my C10H16. Notice both my starting material and my final product have C10H16. My only difference in my final product is I have a C-double bond O. So I have an O2. Here, we're asking about reactivity. So we're asking really about our kinetics. Which one is the faster reaction? Which one's going to be more reactive? So the first thing is, what determines our kinetics? What determines our kinetics? Activation energy. We can predict our activation energy based on what? The difference between, when we're looking at our reaction coordinate diagram, what are we comparing? So our starting material, our product. We're looking at our activation energy. Well, how can we estimate our activation energy? Does this reaction undergo an intermediate? These are the things you should be thinking about. Again, you're not going to pass this class if you can't think like this. You should be thinking about, if I'm thinking about reactivity, what am I thinking about? I'm saying these two alkenes, which one's more reactive towards hydrohalogenation? So hydrohalogenation, what am I adding? H and a Br. Hydrohalogenation. H and a Br. Does that go through an intermediate? Yes. What is that intermediate? Carbocation. So how can I estimate my activation energy? By my carbocation. How stable is my carbocation? Because really, I'm starting with the same material. I'm starting with a pi bond. They may be slightly different in energy depending on if they're more or less substituted, but in this case, they're both the same substitution. So neither is more stable. And we're reacting it with HBr in both cases. So in both of our starting materials, they're going to have roughly the same energy. Our product energy, again, isn't going to be much difference between them. What is going to be different, or what can be different, is our intermediate. And our carbocation intermediate is very unstable. Our activation energy is based on our transition state, but we can have a good idea of what our transition state is based on what our carbocations looks like. Because remember, in the transition state, we're forming the carbocation. So our activation energy, because again, Hammond's postulate, our activation energy is going to be closer in energy to our intermediate than our starting material. So we can get a good idea of what our activation energy looks like based on our intermediate. So our intermediate is our carbocation. So what we can do is compare our two carbocations and see which one's more stable. The more stable carbocation, the lower the activation energy, the more reactive. So looking at the first example, now neither of those two carbons are more or less substituted. But if this carbocation forms, I have the ability to have a rearrangement. That's a secondary carbocation. And a rearrangement would form the more stable tertiary carbocation. If I look at the second example, it's not a double bond. This thing is not quite as calibrated as I want it to be. There we go. If I look at the second example, it doesn't matter which of the two carbons my hydrogen adds to, leaving my carbocation. There is no quick hydrogen transfer that will give me a more stable carbocation. This one's secondary. If I have a rearrangement, in this case, this would be pretty reversible. This would still leave me with a secondary carbocation. We can have a third rearrangement to finally get to the tertiary, but that's going to take more energy. So this first one has the ability to form a more stable carbocation in just one step. So it's going to have a lower activation energy. This is, again, thinking about the reaction I'm asking you about. What's happening in that reaction? And oftentimes, especially if you're going through a carbocation intermediate, we can consider the stability of them. First off, I'm sorry, this was supposed to be an ethyl. So, looking at this mechanism, let's see if I can. So, looking at our mechanism, the first thing we have to consider is what is our nucleophile and what is our electrophile. So, we have a pi bond. How can my pi bond act? It acts as a weak nucleophile or a weak base. It's not going to act as a base here because we do not have a strong enough acid. OH is not a good enough acid. Our pi bond is not strong enough to deprotonate OH. So we would need a really good acid. HBr, that's why that one works. Unlikely that this would act as a base in this case. So it's going to likely act as a nucleophile. That's why when we do our hydration, we use acid H3O+. We don't just use H2O. Because our pi bond is not a strong enough base to deprotonate H2O. It is strong enough to deprotonate H3O+, because we use a strong acid like H2SO4. So we need a strong acid for our double bond to react with. We don't have one. OH is it's one of our more acidic organic acids, but it's not a strong acid. Its pKa is 16. It takes something like sodium hydroxide or stronger to deprotonate it. So we don't have a strong enough acid for our double bond to act as a base because it's very weak. But it can act as a nucleophile, so the question is, what is our electrophile? Our carbon of our alcohol, not electrophilic enough. Not going to attack that carbon, not partial positive enough. But we do have Br2, and though Br2 is nonpolar, it is polarizable. We spent about 15 minutes talking about Br2 in lecture because of this. I don't expect you to memorize this. I expect you to understand that our bigger atoms are polarizable. They can stabilize electrons because they're so big. So because it's polarizable, that means that it can, in the right conditions, form a partial positive and partial negative charge. Because bromine can stabilize the negative charge so well because it's so big. Also, bromine's a great leaving group. So if our double bond attacks one of the bromines, the other bromine's going to leave. It's a good leaving group, and that makes sense. So our electrophile is one of our bromines of our Br2. Doesn't really matter which one, it's one of those. So our pi bond can attack our bromine. That, of course, is going to push off our good leaving group and leave a carbocation. But this has a more stable resonance structure than a carbocation, and that is the bromine pushing its electron density over. To that carbon. This is our key intermediate, the bromonium ion. Now Br is more electronegative, so typically it doesn't want a positive charge. However, it has a full octet, and so does every carbon in the structure. Versus the first resonance structure, which does not have a full octet because that only has 6 electrons. So this doesn't exist very much. This is our more stable resonance structure, and this is what our structure looks like mostly. There's still partial positive charge on that carbon because of this resonance structure, and it's going to be in the more substituted position. Which is why when our nucleophile attacks, it's going to attack in the more substituted position. Again, just like our epoxide, the bromonium ion blocks the face. This is the intermediate that causes the anti-addition. It's anti because this Br minus does not allow the nucleophile to attack from the side. Sterically, it's taking up too much room. If it wasn't for that, then we would get a racemic mixture because we can attack the carbocation on both sides. So we know that the carbocation doesn't exist in any large amount because we don't get a receiving mixture. We only get anti-additions. Also, you never see a rearrangement with this because, again, you have this bromonium ion, and this carbocation, whether it's tertiary or secondary, would be more stable because of resonance. Remember, resonance stabilizes the charge more than induction, primary, secondary, or tertiary. A primary carbocation can exist if it's in resonance. So that is our main intermediate that is causing our observed regiochemistry. Oftentimes in this mechanism, you'll see instead of this being shown, which is our resonance, you'll see just the bromine after this leaves coming back in and attacking. You'll see that in the book sometimes. But it's okay to draw it like this. This is just specifying the resonance structures. Sometimes the resonance structures are shown in the arrows. But this is the same thing. It means the same thing. Now the next step is we have a bond between oxygen and our carbon. The reason why is because alcohol is our solvent. We have a lot more of it than Br minus, which is also floating around. But we have a lot more of our O oxygen than we have of our Br minus. So because of that, that will attack as our nucleophile. Our oxygen has lone pairs. That's where the bond between our carbon and our oxygen is coming from. Now again, we don't have a base in here to deprotonate our hydrogen. So our alcohol must attack neutral. There is nothing in this reaction mixture that's strong enough to deprotonate an OH. Again, reread chapter 3. That talks about pKa. That talks about that we need a base that's stronger than our OH to allow that equilibrium to go farther and actually make an ethoxide. Ethoxides are not necessarily easy to make. And we'll talk about that in chapter 13. So, you have to have a strong enough base to make that. We don't have a strong enough base to make that, so it has to attack neutral. It's going to attack the more substituted position because, again, that resonance structure. And when it does attack the carbon, it's going to open up that ring because carbon cannot have 4 bonds. So essentially, bromine's a leaving group, but it's still going to be attached to carbon too. This isn't quite the full mechanism yet, though. We're not quite finished. Because, remember, our alcohol attacked neutral. So that means we still have a hydrogen on it, and it has a positive charge. You must show all formal charges. You don't necessarily have to draw both enantiomers, but when it's going to attack, it can attack on both faces. It can only attack anti, but we will get the enantiomer. I don't necessarily have to show it attacking twice. So notice my OH is on the opposite side from my bromine. So the last step in my mechanism is the fact that we're not going to isolate an oxygen with a positive charge. And you must show that positive charge. If you don't remember how to calculate formal charge, go back and review that from chapter 1. Because you need to know how to calculate formal charge. If you don't show the formal charge in the mechanism, it's incorrect. So the last step is going to be deprotonating our alcohol. And what's likely going to deprotonate it is another molecule of alcohol, just because we have so much of it, and also Br minus is pretty stable. Because remember, that's why HBr is a strong acid. So it's more likely that our alcohol, another molecule, will come in. And deprotonate our hydrogen of both our compounds. Also the enantiomer, you don't necessarily have to show that. And that forms our 2 compounds. Any questions with that mechanism? That's quiz 1. Going on to quiz 2. Quiz 2, we started looking at triple bonds. And this first reaction, have a good night. We have NaNH2. First thing you should do is look at this reagent. What is this reagent? What is NaNH2? It's a very, very strong base. Not just a strong base, a very, very strong base. If you need, rewrite it. It's not NaNH2, it's Na plus NH2 minus. Nitrogen is somewhat more electronegative than carbon, not very, actually a little bit smaller than carbon, so not stabilizing that negative charge well. The nitrogen wants a proton. However, it's not strong enough to just deprotonate anything. We need a start of acidic hydrogen, and the only start of acidic hydrogen we have is the one on our triple bond. So the first step is going to deprotonate our triple bond. Notice our triple bond is retained. So when we deprotonate our triple bond, we end up with a carbanion, a carbon with a lone pair. How can we describe this compound? How's it going to act? Question. It can act as a strong base if there is any acidic protons present. So we can't do this reaction with alcohols present. That's true. That's true. How else is it going to act? As a nucleophile. So that's true. If we have a electrophile, like an alkyl halide, once we form this, it can react with it. If it's primary or methyl, it's going to act in an SN2 reaction, and we're going to form a new carbon-carbon bond. If it's secondary or tertiary, it's going to act like the strong base it is, and deprotonate the beta carbon and form a double bond. Not typically what we want, because we are trying to build up our carbon source. So that's why this reaction only works with a primary or a methyl alkyl halide. And again, we don't want an alcohol because an alcohol has not a super acidic proton, but compared to this, our pK of our triple bond is 25 versus our pK of our OH is 16. OH is going to push the reaction forward to deprotonate OH. That's a more stable negative charge. Again, reread chapter 3. Acidity is a big part of this class. We'll be talking about it in every chapter. We will always be thinking about an acid-base reaction because we often will use acid-base catalysis. So we need to be able to look at hydrogens and say, is this acidic? Is this not acidic? What will this most likely react with? Do I have any functional groups that are going to react with my base instead of the functional group I want to react with my base? That's going to be an issue. We'll see that with alcohols. Alcohols are acidic. Sometimes they get in the way. It's very important you understand chapter 3. That's why we spent so much time in it in Organic 1. Everything in this class builds. So, again, another thing I want you to note is NaNH2 has a 1 by it and our alkyl halide has a 2. That's because our NaNH2 can adversely react with our alkyl halide and have an elimination. We don't want that side product, so we don't want to mix them together. Once we use up our NaNH2 to form our negatively charged carbon, then we'll throw in our alkyl halide. That's going to form a new bond between, and I'm going to number my carbons, carbon 1 of my triple bond and my carbon 1 of my alkyl halide. And again, it's primary, so this is allowed. We are retaining the triple bond until we do a reaction to get rid of it. Because notice, the lone pair is on the carbon that is sp. It's on an sp carbon. The new bond is coming from the lone pair and the carbon of our alkyl halide. It's not coming from the triple bond. So we are retaining the triple bond. It's coming from the lone pair, not from the pi bonds. The lone pair is the nucleophile. And this is the mechanism of this step. It's just an SN2 mechanism. So we were retaining that triple bond. And again, our triple bonds are linear. So there's my carbon 1. Don't lose a carbon of my electrophile. And it is bonded between carbon 1 of my triple bond. Any questions with that? Now my triple bond looks a little weird here because I just tried to calibrate this thing, but it didn't fully calibrate. But try to be as neat. You don't have to worry about it. Wherever you put your pencil mark, that's where the mark is. Turns out where I put my ink mark on this is slightly off from where it actually shows up. So you should be neat. When I put up my keys, you'll see that my triple bonds are always drawn neatly. Don't lose a carbon here. Your total carbon should be equal to your carbons in your starting material and your carbons in your electrophile. Also notice my electrophile needs a leaving group. You cannot do an SN2 reaction without a partial positive carbon and a leaving group. Otherwise, it's not an electrophile. Okay, looking here, we're starting with our triple bond. Looking to the left, we are reacting it to form a cis double bond. So our reagents to form a cis double bond is our H2 and Lindlar's catalyst. Again, the Lindlar's catalyst is just our palladium, I think it's palladium, our homogeneous metal that's poisoned. I also accept poisoned catalyst, that's fine. You do need the H2 though, otherwise you won't have the hydrogens to add across the double bond. So we added our 2 hydrogens on the same side. It's cis because, again, it's a heterogeneous metal, so whatever side of the triple bond interacts with the metal first, that's the side both hydrogens add on. If we look to the right, we're adding just H2 and just a metal catalyst, no poison, so that means we're going to react both pi bonds. So that's it. You're just fully reducing the compound. Here, for some reason, students lose carbons when you change your geometry at carbons, because here it's linear, and then when we don't have the triple bond anymore, it's not going to be. To avoid that, you're adding 2 hydrogens on each carbon. You're losing your 2 pi bonds. You are not losing any carbons. So to avoid that, just number your carbons. I should have 6 total. What did I do wrong? I have too many carbons. So all you have to do, and my numbering, I wasn't consistent. All you have to do is go ahead and erase one. Now I'm right. That's pretty easy. I don't have to show my hydrogens, but I'm going to have 2 extra hydrogens, 2 on carbon 2 and 2 on carbon 3. I don't have to necessarily show them. And going down in the reaction, we have no difference in our carbons, of course, but we reduce our pi bond, our triple bond, to a double bond. So that means we added 1 hydrogen on each carbon. Again, sorry about the calibration. So that's trans, and we have to use our dissolving metal. This reaction only occurs because sodium metal is so reactive as our Na with our radical. So that is Na, and our hydrogen source is our NH3 liquid. That is not the same as our NaNH2 above. NaNH2 is a stable sodium cation. Our nice stable sodium cation. And our NH2 minus, that's a very strong base. NaNH3 is a very, very reactive source of electron because our sodium metal wants to give up that electron to look like the noble gas before it on the periodic table. So it's a very, very strong source of an electron, not like a sodium with a positive charge, which is very inert, doesn't really do anything. You eat sodium chloride all the time. You have too much, but you eat it all the time. You don't eat sodium metal, you will get badly burned and probably will die. Very different compounds, you must specify that. You probably wouldn't get so far as to die because the water in your mouth would cause the sodium metal to catch on fire. So you'd just catch on fire, you'd get really badly burned. My point is those 2 things are different, and you need to represent that when you show it. And our NH3 here is our source of hydrogen. That's where our hydrogens are coming from. So you have to make sure you show that correctly. So you don't have any confusion, write the Na above the NH3 and put the liquid by it. You can put sodium metal if you want. You can put metal. That's how we usually represent elemental sodium, because it is, of course, a metal. It's a solid. Yeah? No, the 1 and 2 mean you have to add them at separate times. So that's a specific thing. So if sometimes they need to be mixed together for the reaction to occur.
Like with hydroboration oxidation, it's completely wrong if you don't put 1 and 2.
For the hydroboration oxidation, not necessarily.
I remember you saying
it makes it
for something.
It's really important, for example, up here, NaNH2, we don't want to mix it with our electrophile because it could act as a base. Really important there. It's really important when we are forming a triple bond that we don't mix our NaNH2 with water, because NaNH2, again, what we're thinking about is our acid-base reaction. What side does the equilibrium lie on? OH minus. OH minus, not strong enough to deprotonate a triple bond. Oxygen stabilizes a negative charge better than nitrogen. Again, this is where chapter 3 is really important. So that's why we can't mix NH2 minus and H2O, because NH2 minus is a stronger base than OH minus. So those times it's really important, because if we use up our NH2 reacting it with water, it's not going to react with what we want it to. In the case of our BH3THF and our peroxide sodium hydroxide, the book kind of goes both ways. It's probably safe to put the 1 and the 2 because of the oxidation reaction. Could adversely react with our BH3 before we want it to, which would stop the addition from occurring. But sometimes the book doesn't put it, so I'm not as strict with that one. Though, for that case, you always want to make sure, if you have the possibility of byproducts, you might want to have them not happen. But the oxidation is likely not to happen to just the BH3. So the book doesn't always put a 1 and 2. If we do our mercuration, demercuration, that one's really important. We have the 1 and 2. Sodium borohydride we'll talk about in a lot of detail in the next coming chapter. And we're going to learn how sodium borohydride is starts with H negative. It's pretty reactive. So we don't want to add it until we want that to react. So things like that, and we are going to talk about when a 1 and a 2 is necessary. And usually it's reasons like this. So it's all about when we want things to react. Now H2 and Lindlar's catalyst, those two things have to be together. We will not get a reaction until we have our catalyst. It takes too much energy. We need to lower that activation energy. So you can mix your pi bond with H2 at regular temperature as much as you want. Nothing's going to happen to you at that catalyst. So then a 1 and a 2 wouldn't be very useful. You'd just be wasting your time. So that's what the 1 and 2 mean. So like here, very important that our NaNH2 is not mixed with water. Because then we just wouldn't get a reaction. We just get this. And that's not very useful. You're welcome. It's a good question. So looking at this one, the question is, which one's going to lead to the triple bond? So first off, we're starting with no pi bonds and we're forming 2. So it means we're doing 2 eliminations, which means we have to make room for those pi bonds. Notice this carbon, it has 0 hydrogens. Notice this carbon, it has 1 hydrogen. If this carbon has 2 hydrogens, how are we going to get rid of 2 hydrogens? To make room. If this carbon has 2 hydrogens and only has 1 left over, okay, our bromine can leave, but the other hydrogen can't. That's why we need 2 beta hydrogens and 2 leaving groups. So these 2 don't have 2 leaving groups. We can form a double bond, but we can't form a triple bond with them. We don't have room to make room for those 2 pi bonds. Remember, carbon can't have an expanded octet, so we can only have 4 total bonds. Now, if we look at the next 2, they both have 2 leaving groups, but there is a problem with this one. What's the problem here? The bromine's in the wrong place. We need our two leaving groups to be to where we can get a triple bond between, let's call them carbons 1 and 2. So sure, we have a leaving group on carbon 2. We can deprotonate carbon 1, but how do we get that other hydrogen off of carbon 1? It's not a good leaving group. There's no other leaving group on carbon 2. And we can't form a triple bond between here because this carbon already has 2 R groups. Remember, a triple bond can only have 1 R group. Otherwise, we'd have 5 bonds to carbon. So that bromine's in the wrong place. Not only do we need 2 leaving groups, but we need them in the right place. Our options are to have both leaving groups on carbon 1, both leaving groups on carbon 2, or 1 leaving group on carbon 1 and 1 leaving group on carbon 2. That's our 3 main options. And this is the only one that goes with them. So for this example, our 2 leaving groups are both on carbon 1. So that means our 2 beta hydrogens are going to be coming from carbon 2. If our 2 leaving groups were on one on carbon 1 and one on carbon 2, then our 2 beta hydrogens would be on both carbons. But the mechanism is pretty much the same. So the mechanism is just 2 E2 reactions consecutively. Now remember, our E2 reactions have to occur anti, but other than that, it's just 2 E2 reactions. So starting with our starting material. We have our NH2 minus. We just talked about NH2 minus. It's a strong base, so it's going to deprotonate something. The only beta hydrogen we have is carbon 2. And that has 2 hydrogens. So our first step is going to be our first E2 reaction. Deprotonating there we go. Deprotonating one of our hydrogens on carbon 2. That leaves another hydrogen. And one of our bromines left, but that leaves another bromine. So our second step is the same thing to form our triple bond. So this is why we need 2 beta hydrogens and 2 leaving groups on our 2 carbons that we're forming the triple bond. Now typically, we use a bit of excess of our NaNH2. So what will typically happen to drive this reaction forward is, since we use more of our reagent, Le Chatelier's principle, more starting material pushes the reaction forward, typically what we'll get, and I wasn't real strict about this in the mechanism, but what we'll get is a deprotonation, just like we would if we were trying to get our carbanion. But we can't isolate the carbanion. And also we need a neutralized NaNH2. So typically what we'll do is throw in water. That's why it's there second. And the water is going to act as a base to reprotonate our triple bond. Because again, that carbon nucleophile is also a very strong base. If we didn't have access, in theory we could stop here, but really in practice we wouldn't get a high yield, so we use excess to get a high yield. So usually we'll go all the way here until we react it long enough to where we don't have any starting material left, and then we'll neutralize it with some H2O, maybe a small amount of acid to neutralize any leftover NH2. And that's the kind of thing you would do in the lab when you dropwise add a little bit of water and acid to your reaction. You probably don't want to add this too fast. It would probably be a really exothermic reaction if you just pour water in. So you probably have to drip it in. This is practical things not on the test, but practical things in lab you will be doing. Any question with that mechanism? I was really just looking for this first 3 steps. Okay, here we're naming. We will have some naming on the exam. We want our triple bond to be the lowest numbering system possible. And we want our parent to contain our triple bond. And in this case, it's going to contain our double bond as well. So our triple bond, I've seen a couple of people do this. Either skip one of our carbons. Remember, each carbon that's the end of the 3 bonds is a carbon. So I know it's linear, but this is carbon 3, this is carbon 4. Don't skip one of those carbons. Very common mistake. 5, 6, 7, 8, and 9. So the beginning of the carbon and the end, we have 2 carbons here. So a lot of students are skipping one of the carbons, so be careful there. So we have a total of 9. Then we have an ene and an yne. So we're just going to put both of those. So no, our ene is on 1. And we do want that 1 because a double bond could be anywhere. And our yne starts on 3. So that's it. We just put them all in the name. And this is one of the cases where it's probably a little better to put your numbers right by the ene and the yne since we have both of them. But if we just had the triple bond, it was just ene, we could put it in there as well. If we had 2 enes, it would be a diene. If we had 3 enes, it would be a triene. Again, we want the lowest numbering system possible for the triple bonds. It doesn't really matter about anything else. Then our cyclohexyl group, remember, if it's a substituent, it's no longer an ene, it's a YL. And don't forget the cyclo, that's really important. And this is a pent, I just said hex. Cyclopentyl. But don't forget the YL because it's a substituent. And don't forget the cyclo because this is pentyl. If we don't put the cyclo. And of course that's on carbon 5. And then the last thing, this is going to be S. So you need to specify stereochemistry if geometry is specified. Now, my double bond is not an isomer. It's neither a cis-trans isomer or an E or Z because we have 2 hydrogens on carbon 1. So you don't have to worry about specifying a double bond because it doesn't have a stereoisomer. So for S, of course, our number 4 is hydrogen. It's going back. But then if we look at our carbons, we have carbon, carbon, carbon. That's a tie. So we're going to go to our tiebreakers. This is attached to 2 carbons and a hydrogen. This is attached to a carbon and 2 hydrogens. This is attached, remember, a triple bond to 3 carbons. So, of course, carbons are the same. Then we have carbon, carbon, hydrogen. Carbon wins, so this is going to be our number 1. And then between these 2, carbon versus hydrogen, this one's going to be number 2, and this one's going to be number 3. So that's 1, 2, and 3. On the uploaded sheet, I have these in different colors. I only have 2 colors to work with here. 4 is going back, so we don't have to worry about that. So we're turning that counterclockwise, so that's S. And again, a nice little trick. S, to write the S, you have to go counterclockwise. To write the R, you have to draw it clockwise. But 4 has to be back. Here is a synthesis. This is not a mechanism. There is no one reaction that can get us from our starting material to our final product. We're going to have to do multiple reactions. Each reaction does have a mechanism, but I'm not asking you for mechanisms. And every intermediate should be isolatable in a synthesis. So we will not typically have any charged intermediates because they're not typically isolated. So no carbocations for sure. You cannot isolate a carbocation. But typically it's hard to isolate even a hydroxide because water, it'll typically find it from somewhere. And there's usually even a trace amount of acid in things, so you have to be careful. So what we see is we have a double bond. First off, you always want to check, is there any difference in carbon source? And the answer is there's not. There's the same amount of carbons in my starting material and my product. And at this point, of course, in this quiz, there would have been. See this cyclopentane? The cyclopentone side chain? It doesn't matter. We're not doing anything at those carbons. Ignore it. I can have a bar there and it wouldn't make a difference. What you can do with that side chain is to help you find where your starting carbons are in your final product. So it's oriented the same way. I'm nice. I put it oriented the same way. I could have given your product flipped in space because remember, molecules can flip. I didn't. I oriented everything the same way. But if that does happen, you can use something like carbon 4 with the cyclopentyl to determine where your original carbons were. And just be, when you're numbering, just be consistent. So what I see is I had a pi bond between carbons 1 and 2, and now I don't have a pi bond anywhere, but I have functionality on carbon 3, specifically in alcohol. Well, to get functionality on carbon 3, I have to get functionality towards carbon 3, because right now carbon 3 just has 2 hydrogens on it, doesn't have a partial charge. It's not an electrophile. Carbon 3 isn't. It's not a nucleophile. We don't have a lone pair. But we do have reactivity between carbon 1 and 2. So we can work with that. We can put a leaving group on carbon 2, because then we can get a double bond between carbons 2 and 3. So that's going to be our strategy. Technically, we can put an alcohol, but not a good leaving group. So typically, we'll do halogens. So we can do an addition with HBr. We want our bromine on carbon 2 because that's getting us closer to our reactivity on carbon 3. So we're trying to get closer to carbon 3. If we put bromine on carbon 1, that's taking our reactivity further from carbon 3. So that's not really very useful. So we want our Markovnikov addition. We don't need to add anything else. It's going to give us our bromine added to, not carbon 3. I've been talking about it for too long. On carbon 2. So still we don't have functionality on carbon 3, but we're getting closer because now carbon 3 is a beta hydrogen. It's a beta carbon, so we can deprotonate that hydrogen. We want to get our double bond between carbons 2 and 3. That would be our more substituted double bond. And we can do that because we know our selectivity of our reagents. So to get the most substituted double bond, we need a smaller strong base. We need it strong because we're forcing it to go through an E2. Because it could go through an E1. But an E1, we might get byproducts and it could be a pain. Though technically we could probably go through an E1 because we only ever get our most substituted in E1, but we do have more control in E2. So that's why we want our strong base. Our smaller base is going to be able to deprotonate both beta hydrogens. So we won't have any big difference in activation energy, but we will get a lower energy product, which is why we get our most substituted. Our least substituted is a higher energy product. So if we have the chance to go through the same activation energy for our 2 routes, and our only difference is our product, we're going to get our thermodynamic product. So that's why we use our small, strong base. Now that we have our double bond, we have functionality on carbon 3. So we can add a hydrogen on carbon 2, which is what we have in our final product, and we can add an alcohol on carbon 3 because we have reagents to do that. And that's our hydroboration oxidation. So our BH3. We do need THF if we're using BH3. followed by our peroxide and sodium hydroxide. And that's our route. Now we will get both enantiomers if I only wanted one. I don't really have a good route to do that. But that's okay. Sometimes you do have limitations in synthesis. That's quiz 2. Any questions? Is it starting to make sense? And you got to be able to do this on your own. Not just with me up here telling it to you. Okay, looking at carbon 3, sorry. Quiz 3. Wait, we just did quiz 3? No. Why didn't it open quiz 3? Oh no. I think I just replaced quiz 3. I did replace quiz 3 with quiz 2. Let's go through quiz 4 and then I'm going to go get quiz 3 from my computer. Because I need it in PDF form, otherwise I can't open it. Okay, so quiz 4. First off, Br2 and HNU. The only time we talked about using light was through radical bromination, but heat would work too. We do need either heat or light. So in synthesis, don't just put Br2. We do need heat or light to form radicals. It does take energy to form a radical. So the question is, which distinct mono, meaning only one halogen in each compound, are we going to form? So this goes through the fact that once we form our bromine radical, we can get a hydrogen abstraction. It's not strong enough to get a methyl abstraction, so we should have the same number of carbons in our starting material in all of our products. Otherwise, it's not a possible product. So the question is, we can get a bromination at any carbon that has a hydrogen, at least in theory. So we don't have a hydrogen here, so we can't get a bromination in that position. But we do have a hydrogen in all our other positions. So again, all of our answers are going to have the same amount of carbons. So we can get a halogenation, a radical bromination on carbon 1. Or the other two CH3 groups, but those all end up to be the same product. We can get our bromination on carbon 2. I mean, not on carbon 2, we don't have a hydrogen, on carbon 3. But notice this is a stereocenter, so we're going to get both enantiomers. And then lastly, we also have a hydrogen on carbon 4. So we could, in theory, get the bromination on carbon 4. Now we know bromination is a lot more selective. So it's really unlikely that we're going to get these two brominations because that would go through a primary radical, which would be too high of an activation energy. So we actually only expect to get these two products in a pretty high yield because that would be our most stable radical, which it would be secondary. Chlorination isn't as selective. We would expect to get all of these products if we were reacting without chlorine. But with Br2, this is really the only two products that we expect. These are all possible exchange products. Now this one, what's our answer? No reaction, I2 is not fast enough. Remember, we went through all those thermodynamics. So this only reacts with CO2 and Br2. I2 is non-spontaneous. Our delta G is positive. Here, guys, It's HBr and peroxide. It's just our anti-Markovnikov addition we've been doing since chapter 9. So we're adding our Br on the most substituted. This is supposed to be a really, really easy question. Remember, your test is going to have all reagents from all chapters, so you need to start being able to recognize them. So, of course, we do form both enantiomers because we're going through that radical intermediate. Now, D, NBS is our source of bromine radical with very little Br2. What that means is we don't expect to get addition across the pi bond of Br2. If we use these reagents, which would be Br2 and H nu, we would expect our addition of a bromine on each of the carbons of our double bond. But NBS prevents that by never having a huge amount of Br2 present. So you need to recognize NBS as being used when we want to get a Lilic bromination. Now technically we can use NBS for any bromination because we have a source of bromine radical. So it's fine, it'll work for any bromination. It would have worked for this reaction above. If I wanted to put NBS, it would work. We'd still get these two products. But it's especially important when we have a double bond because we want to get the radical bromination, not the addition of Br2. So if you put the addition of Br2, I gave you a good bit of credit. But what I'm looking for is our Lilic bromination because we still want to form our radical. Now, before I go on and I look at that, this is not possible because this would mean that we're adding a bromine and a hydrogen across the double bond, and we don't have any hydrogen. NBS doesn't have any hydrogen that is available. It doesn't have an acidic hydrogen for our double bond to react with. So we can't add a hydrogen if we don't have a hydrogen in there. Again, remember my cookies analogy. If I'm baking cookies and I don't put pecans in my cookies, I'm not going to have pecans in my final cookies. I got to put pecans in my dough to get pecans in my cookies. And if you do have pecans in your cookies in the end and you didn't put it in, you probably should leave the house because someone's probably in there. And you don't want to take any chances. Law of conservation of matter. You can only get out what you put in. We're not putting in hydrogen. We can't add extra hydrogen. Now, that's not to say that you can't consider, okay, there's hydrogen in the atmosphere, but not enough to react. That's a very stable hydrogen. So remember, we have to put things in. So what we have is we form our radical reaction. We're still going to form our most stable radical, but in this case, our most stable radical is going to be the one in resonance. Yes, sure, this particular one is tertiary, but a radical that's in resonance with a double bond, a Lilic radical, or a benzylic radical, a radical that is in resonance with a benzene ring, is going to be more stable than a normal tertiary radical. So we're always going to form that radical in more amount because resonance stabilizes more than induction. So this will lead to one of our products. And of course, that enantiomer. But also, you need to consider your resonance structure. Because remember, this isn't an interconverting structure. So this resonance structure can also lead. Oh gosh, I'm joking, guys. There's no enantiomer. This is not a stereocenter. There's no substitution on that ring. So those are your two possible products. Likely you might get a little bit more of this one because this is going to be our more contributing resonance structure because our radical is more stable. It's tertiary versus primary. But the difference might not be enough to where we'd see a difference in the amount of product made. It might be a difference of, let's say, 53% and like 47. So it might not be a big difference. As far as resonance, remember, when we're showing arrows for our radicals, we show the fishhook arrows. And the fishhook arrows only show the movement of one electron. So that means that if we have 3 electrons that are participating in resonance, we need to have 3 arrows. our resonance can only be between carbons that have unhybridized p orbitals. That is this carbon, this carbon, this carbon, this carbon, and this carbon. This carbon has a full octet, only hybridized orbitals. You can't push electrons onto that carbon because we have to have a leaving group. Any carbons that are single bonded that don't have lone pairs are not going to participate in resonance. So no sp3 carbons. So we have our sp2 carbons, they all have unhybridized p orbitals. If I number this, that means carbons 3, 4, 5, 6, and 7 all have unhybridized p orbitals. So one resonance structure, I can form a pi bond between carbon 3 with our radical, and then with one of the electrons of my pi bond, that's at carbon 4, my other electron of my pi bond between 4 and 5 have to go somewhere, so it's going to go in 5. So that's 3 electrons. So that's one resonance structure. And then I also have a conjugation with another pi bond, so I'm going to have the same type of resonance structure, where we're going to have a pi bond form between 5 and 6 from my radical, and then one of my electrons from my pi bond between 6 and 7, and then that other electron has to go somewhere, so 7 is the only possible place. That CH3 group is sp3 and it's fully an octet and does not have an unhybridized p orbital. So what this is showing is my electrons are shared between carbons 3, 4, 5, 6, and 7. Be clear with your arrows for resonance. Notice the base of my arrow is coming from either lone pair or from my pi bond. Okay, here I only want the propagation steps. I already initiated for you. You have the bromine radical. You don't need to do an initiation. So our first step is going to be a hydrogen abstraction to form a carbon radical. Because remember, this is not correct. The homolytic cleavage of carbon and hydrogen, very unstable. It would take too much energy. That does not happen. The first radical that has to form is our initiator. Br2 is an okay initiator. At least when we have lighter heat. So once that bromine forms, then we can have a hydrogen abstraction, where we form a bromine-hydrogen bond by taking one of the electrons from the bond between carbon and hydrogen and the radical on bromine. Then we have to take the other electron between the bond between carbon and hydrogen and put it onto our carbon. And of course, we're going to form our more substituted radical. And this forms HBr. Now technically, I want a propagation reaction. So you could show the coupling of your bromine radical and your carbon radical, but that would be a termination, and I was looking for propagation steps. So the next step in your propagation step would be a bromine extraction from Br2, because again, remember, there's Br2 floating around. There has to be. We don't want a lot of bromine radical. So that can happen from forming a bond between bromine and our carbon radical, and then that forms, guess what, a new bromine radical, which could then react with another carbon-containing molecule. So the propagation continues. So in this case, I only wanted the propagation steps. Now it's not untrue that this radical can react with this radical in a coupling with one this, but I was looking for propagation. If this reacted with a bromine radical, that would be a termination. And that would stop the process. Of course it happens, but you want it to happen when you're done with the reaction, so you can continue the propagation process. That's why you keep the amount of bromine radical low. And this is a hydrogen-bromine bond. I'm sorry, it's so dirty. Okay, a synthesis. First off, we have the same number of carbons in my starting material and my line product. My difference is in alcohol. What can you say about your starting material? Is it an electrophile, a nucleophile? It's nothing. It has no functionality. At this point, it will combust, and it will do a radical halogenation. That is it. That is your only option. You can react it with Br2 and light or heat. You can react it with CO2 and light and heat. You can react it with NBS and light. All of those are sources of bromine radical. We can do CO2 isn't a source of bromine radical. We don't want to use CO2 because we're going to get a bunch of products. So it's best to go through bromination. And remember, we're going to form our most substituted halogen. None of the halogenations are going to form the least substituted as major. It's always going to form the most substituted. We're always going to go through the most stable radical. But chlorination will form a good bit of the other ones. With bromination, we'll get almost 100% yield of just the most substituted. But we can't ever, not with these reactions, we won't ever favor the formation of the least substituted. So that means we're going to get the most substituted bromination. Again, you could use NBS or you can use Br2. You must use light or heat. Those are fine. So what we're going to form is now we have it functionality. We have an electrophile. We can do an elimination. We can do a substitution. We can do things with this. We can't do anything with starting material. This is the only reagents that the starting material react with. You can put in Na-NH2 minus. It won't do anything. There's no acidic hydrogen, so you can put it in. Mix it all you want. You can heat it up really high. You might decompose it, but you won't react it with anything. It might break apart. It might turn into sludge. Then you won't be able to do anything with it. There's not a lot you can do with an unsaturated hydrocarbon that has no functionality other than burn it. So we need to put functionality onto it. That's always the case. If you see something with no functional groups, it's not going to react with anything but our radical bromination or radical halogenations. Or we can burn it, which we don't typically want for synthesis, because what are we going to do with CO2 and H2O? Which is our products from burning. So we want to build up our compound, not break it apart. So what we have is now we have a functional group. We need functionality on carbon 1. We have functionality right now on carbon 2. But hey, we can get functionality on carbon 1 because we can do an elimination and favor our least substituted double bond. So to favor our least substituted double bond, we must go through an E2 because E1 always favors our most substituted. So we can use our strong big base. And the reason why this works, just a reminder from chapter 8. Here, our big base sterically can only really deprotonate carbon 1 because there's more sterics to deprotonate carbon 2. So in that case, if we're comparing our pathways, we'll call this C2. It's not as big of a difference as I wanted to show. Let's call this C1. Even though our least substituted double bond isn't as stable, because our big strong base can only deprotonate C1, that's what we're going to form. Again, we're comparing to our smaller base, and we have a smaller base, our activation energies are pretty much equal. So we're actually utilizing our sterics to make our reactions do what we want. We're utilizing what nature wants to do and using it to our advantage. We do that all the time in chemistry. We're not making nature do something it doesn't want to do. We're just exploiting it, which is what a good chemist does. What wants to happen naturally? And sometimes we'll try to go against nature by putting more pressure and putting more temperature, but there's only so much we can do. We have to really take what nature wants to do based on sterics and electronics and run with it. And that's understanding organic chemistry. So now we have functionality on carbon 1. Now we want an alcohol on carbon 1. That's our least substituted addition of H and OH. So that's our BH3 and THF again. So I see that the chapter 12 assignment helped a lot of you. Many of you saw that you had to get to this double bond. You just had a hard time getting there. So I'm glad you're seeing that. Okay, let me go run to my office and grab quiz 3 again, because I paused this. I will be right back. So, starting with our triple bond again. Let's look to the left. We're doing ozonolysis. That means that we are breaking the 2 pi bonds and the sigma bond between our 2 carbons of our triple bond. So I'm gonna call that 4 and 5, because it's a little bit easier to draw, but it doesn't matter. So we're breaking fully the bond between 4 and 5. Now, because we have 2 pi bonds, we're going to get 2 additions of our ozonolysis. So that means we're going to have 2 oxygens in our final products on each carbon. Again, numbering can really help. So that means I'm going to have a C double bond O on carbon 4 and an OH. That's my 2 alcohols. Plus, carbon 5 already had a hydrogen because it's our terminal. So we don't form C double bond O H OH. That's not very stable. It's gonna reform itself to CO2. So anytime you have a terminal alkyne, you're gonna form the carboxylic acid plus CO2. If it's internal, you'll form 2 carboxylic acids. But it's just because CO2 is so much more stable. So that's actually our carbon 5. Again, notice though, total, we started with 6 overall carbons, and our 2 compounds combined have 6 overall carbons. Now CO2 is going to float away, but if we have a closed system, we still have CO2 in our reaction. But CO2 is a gas, so it will evaporate. Now looking to the right, we have 1 equivalent of Br2. So that means we're adding a bromine on carbon 4 and a bromine on carbon 5. We're only adding 1 equivalent of Br2, so that means we're only using 1 pi bond. So we're going to retain a pi bond. We're starting with 2 pi bonds. Because this mechanism is not quite the same as our regular Br2 mechanism because of the pi bond, but because we're needing it's a 3-molecule reaction. 1 bromine Br2 comes from one side, the other bromine Br2 comes from the other. So our major is going to be the trans with our bromines on opposite sides of the double bond. It won't matter if we get our excess, because then we'd get 2 bromines on each carbon. But it matters when we go through this only 1 equivalent. Again, I don't want to lose any carbons. So, still writing my numbers. So I'm adding bromine, and trans is going to be my major. CCl4, that's just my non-nucleophilic solvent. The reason why it's useful is it won't react with my compound. So it won't be, it's still just going to be in there. We're going to evaporate it. I'm going to remove it. Now if we look down, we're adding an excess of HBr. So we're adding H on one carbon and a bromine on the other. We have an excess, so we're doing that twice. Now HBr, when we don't have peroxide present, is it Markovnikov or anti? Markovnikov. So both of our bromines are going to add in Markovnikov position. The common mistake is putting one bromine on one and one bromine on the other. That's Br2. Our H adds in the least substituted, our bromines add in the most. If we add peroxide, both of our bromines would add in the least substituted. Unless it's an internal alkyne, we have no control. We're going to get a big mixture. So we don't retain a pi bond because we have excess, so we're going to get two additions. And both of my bromines are going to add Markovnikov. And of course we had two hydrogens on carbon 5. I don't need to show that, but we know because we look in our starting material, carbon 5 only has one hydrogen, and in my product carbon 5 has 3. So we know we added 2. You can always draw your hydrogens at your reactive centers. I don't really care about my hydrogens anywhere else. We know they're there. Or you can draw your hydrogens in if it really helps you. Just make sure your product is easy for me to read. Here we're using our R2BH. Now here we're not using BH3 because of possible byproducts. That's why we use the R2BH. So we only have one hydrogen available. And this is going to be our adding of H and OH, and it's going to be our anti-Markovnikov addition. So that means our alcohol is going to add in the most substituted. This is our enol. We get the one addition. But that's not isolated. We're going to have our tautomerization to form our, in this case, aldehyde, because carbon 1 already has a hydrogen. So that's what we draw. And typically with an aldehyde, you put the hydrogen. You don't have to, but it's pretty common that you draw that hydrogen for the aldehyde. That's a hydrogen. I'm sorry about the way this thing is showing up. If it was our acid catalyzed hydration with our mercury sulfate because of catalysis, then we would still get our CO-N-O, but it would be in substitute. So we're only getting one addition, but we get this tautomerization. Like this. Now I'm sorry about this. This is basic conditions and I have acid. Pay attention to what's here as an H3O+. So I'm sorry about that. You can always raise your hand and ask me about that if you see that when you're taking it. So here we're looking at the tautomerization under acidic conditions, though you should be able to draw it under basic conditions as well. Remember, under acidic conditions, we only form positive charge. Because acidic conditions mean we have a strong acid, so a strong base will form in the presence of a strong acid. The only negative charge that forms is our conjugate base of our strong acid. We're using H2SO4. Our conjugate base of H2SO4 is very stable. That's what makes H2SO4 a strong acid. So we don't really need to worry about it. I'm assuming it's H2SO4 because it's a strong acid. It might be H3PO4, I don't know. But I have the H3O+, so I know it's a strong acid. So first off, we have an acid. An acid is a source of our H+, so something is going to attack it. The arrow is going to be pointing to our hydrogen of our H+, because it has a very, well, really, remember, H3O+ is the same as saying H+ and H2O. So that means we have a proton. Proton has no electrons. The base of the arrow cannot come from an acid. It can't even come from the oxygen on the H3O+, Because even though it has a lone pair, that oxygen already has a positive charge, it will not give up more electrons. It doesn't have available electrons. Just because something has a lone pair doesn't mean they're available. It has to have available electrons. So, first I want to show something that's not quite right, but not necessarily wrong based on any of our rules. Now, what is wrong based on any of our rules is my base of my arrow coming from my acid. There's no electrons in my acid. That's what makes an acid an acid. That's not correct. So we have our very partial positive hydrogen. Now, just because my oxygen has a formal positive charge does not mean it doesn't have a partial negative charge. The formal charge is its actual formal charge. The partial charge is based on electronegativity. Oxygen is more electronegative than hydrogen. That never changes. Oxygen will always have a partial negative charge when we're talking about polarity. That is inherent to oxygen. Everyone understands that? Something can have a partial charge of positive but still be a full charge of positive but still have a partial negative charge. It's still the most electronegative atom. So that means that my hydrogen can be attacked. So looking at my reaction, my starting material, where do I have a source of electrons? Well, there's two places. I have a source of electrons in my pi bond, which is what we're going to see. But I also have a source of electrons in my oxygen. And we will see sometimes when our alcohol will react with an acid. We'll see this in a lot of reactions, especially in the next chapter, chapter 13. The problem is, well, once we protonate this, we can't form our final product. This is an okay leaving group, but we won't get an SN2 reaction and an sp2 carbon. So what's going to happen if this forms? And one thing to note, we're drawing out the mechanism to get from our starting material to our final product. That doesn't mean this isn't happening. It's likely happening, but it's highly reversible, and that's all that's going to happen. Water is going to come back in because no further reaction is going to occur with this compound. The only other thing that can happen is water is going to come back in and reform our starting material. That's it. And that's probably happening because this is highly reversible. It's probably going on back and forth, back and forth. Equilibrium lies with this being protonated and slipping with this. So this is likely occurring. It doesn't lead to our final product. So there's nothing inherently wrong with drawing this. These electrons will be attracted to our acid, but nothing else is going to happen. We don't have a nucleophile to attack here. Nothing's really going to attack here because it's sp2, so we wouldn't get an SN2 reaction. We don't have any beta hydrogens to get a triple bond, and nothing strong enough to do that. So nothing else is going to happen. So yeah, this is probably competing and going on, but it's not going to lead to our final product. And usually when we're drawing our mechanism, we're drawing our main mechanism. But that doesn't mean other things aren't maybe happening. It's always something to think about. So that's not going to lead to our product. But we have another source of electrons. Remember, our pi bond is a weak base. And H3O plus is a strong acid. So that's going to happen. I don't know where that big line just came from. Ignore it. Now, typically, you would form your tertiary carbocation. But that's not our most stable carbocation. Our most stable carbocation is going to be the secondary because it can form resonance structures with the alcohol. The tertiary can't form a resonance structure, so our most stable carbocation is the one that's right next to our alcohol. So we are still forming our most stable carbocation. It's just not tertiary carbocation. Because remember, resonance will stabilize more. So now we have a carbocation And it is in resonance with the electrons of our oxygen, because we have a positive charge near a lone pair. And again, our more stable resonance structure will be the one with the positive charge on the oxygen, because every atom has a complete octet in that structure. So this one is going to be more contributing. Oh, this one's still contributing. This one's more contributing. And then this resonance structure can easily lead to our final product, because we can deprotonate that hydrogen. We have water floating around. We have H3O+, we also have water. Also note, this hydrogen is already there. It was there in the starting material. And that forms our final product. Now, in the basic reaction, we won't form positive charge, we only have one negative charge. And here we're only forming positive charge. Any questions? Okay, so two more syntheses. First thing to note, it's pretty apparent, we have a lot more carbons in our final product. Also, again, the fact that we have that cyclopentane ring doesn't really do anything with the reaction. Nothing's happening on those carbons, but it does help us to identify where our starting material is in our final product. Because the cyclopentane ring is pretty clear where it is in the starting material in the product. So find your original carbons. That'll really help. So clearly, if I label 1 and 2 my starting material as I did, this must be carbons 1 and 2. Because carbon 1 has that cyclopentane ring, and there it is. So that means we're forming a new carbon-carbon bond between carbon 2 and we're going to call this carbon 3, 4, 5, 6, 7, and carbon 3. So we're forming a new carbon-carbon bond between 2 and 3. The only way we've talked about so far to form a new carbon-carbon bond is to form a triple bond and deprotonate it. Now remember, we can't deprotonate a double bond because we don't have a strong enough base to do that. Our pKa of a hydrogen of an sp2 carbon is around 44 versus a triple bond around 25. 44 is very high pKa, basically not acidic, not very useful acidity-wise. So we have to form the triple bond. Once we form the triple bond, we can form our new carbon-carbon bond. Now in chapter 13, we're going to find new ways to make carbon-carbon bonds. Different route than the one we've been doing. Still going to go through a carbon nucleophile. We need a carbon that can attack. So we need to form a carbon nucleophile, which means a carbanion. So to form our triple bond, what do we need? So we need 2 leaving groups. We can get 2 leaving groups by not HBr because that'll add a hydrogen and a bromine. It's not useful. So we need Br2. And we want the addition reaction to occur. And usually we'll use our carbon tetrachloride. That's just our solvent. It helps the reaction go forward. So that forms our bromines. 1 on carbon 1, 1 on carbon 2. Yes? This isn't a radical reaction. Now remember, we talked about our additions and our thermodynamics of addition reactions, and that we usually keep those not too high in temperature. Go back and review that. It's in the first couple of slides in chapter 9 when we started talking about addition. So, and of course we're going to form both enantiomers, but that's irrelevant, really, because we're going to be able to get the triple bond. We won't have any stereochemistry. So once we have our 2 leaving groups, now we can form our triple bond. And like I said, I want to see the full intermediates. And here's where I got to have H2O second, because otherwise it would react with our strong base. So that forms our triple bond between 1 and 2. Don't lose any carbons here. It's typically understood to be in excess. You can write it, but usually it's just understood to be in excess. If it's not, then you won't get a full reaction. So now once we have this, then we want to deprotonate it. Technically in your book sometimes it might skip this H2O step, but I want to see your triple bond because I want to see that you're understanding it. Really, I can take my excess NaNH2 and then just add my alkyl halide. But I want to see your triple bond. And I just want to see it so I know you understand where you're going. And also, if you are going wrong, I can get more credit. If you don't write down what you're thinking, I don't know what you're thinking. You're like, well, Dr. Carr says I thought this did this. Well, I don't know what you thought it did. You didn't show me what you thought it did. So I need to see everything. I can't figure out what you were thinking. So I'm going to, again, add some NaNH2, again, a bit excess. We want it to fully deprotonate. And now I'm going to add my alkyl halide. So my leaving group needs to be on which carbon? Where is my new carbon-carbon bond? Okay, so my leaving group has to be on which carbon? 3. That's where my new carbon-carbon bond is. My carbon nucleophile, my lone pair, is going to be on carbon 2. And it's going to attack the carbon that has my leaving group. So my leaving group has to be on the carbon where my new bond formed. And my leaving group can be chlorine, bromine, or iodine. It's up to you. So again, here's where numbering can get really useful so you don't miss a carbon. If I say my chlorine's here, that's going to be my carbon 3. And my CH3 group is on carbon 5. That's 7. See my numbering? A lot of students got to this point, but didn't connect that CH3 group in the right place. They put it on carbon 4, number, and just be consistent. Because really, I can put or CH2Cl, and that's going to give me the same answer. So you just have to make sure that this is connected the same. You're not doing anything. Carbon 3 is primary, so this is a viable route. Remember, our carbon 3 has to be primary. So remember, this retains our triple bond. We form our new bond between carbon 2 and carbon 3. There we go. Now our final product has a single bond between carbon 1 and carbon 2, but we can do that by using our H2 and platinum, palladium. I know I just said platinum and wrote palladium, but platinum, palladium, or nickel. Those are our common metal catalysts. Any one I would accept, platinum, palladium, or nickel. Now our last one, again, starting with a triple bond. Nice, we're starting with a triple bond here. It's really simple. Technically, there's 2 routes to this. I'm going to go through the easiest route with the less steps, but the other route has 2 more steps, but it's not really that much harder. So here I'm just starting with acetylene. That could be any carbons. But we know our 2 carbons in our starting material can't be these 2, because this would have to be a secondary alkyl halide. Because if we form this new carbon-carbon bond, this alkyl halide would have to be secondary. Our alkyl halides have to be primary. So our 2 carbons could be these 2, or it could be these 2. I'm going to do our carbons to be these 2, but you could also go through a route where your 2 carbons are these 2. I'll show you both routes. So if I call this my starting carbons here, that means I formed a new bond here and a new bond here. And you can do that because I have 2 hydrogens on acetylene. So I could use my Na. I already have a triple bond. My NaNH2. That will deprotonate one of either carbon 1 or carbon 2. Let's say it's deprotonating carbon 1 first. So then I can throw in my alkyl halide, where my chlorine is going to be on carbon 1. Or iodine or bromine. So that'll form a new bond between red carbon 1 and my blue carbon 1. And of course in the key, I use more colors than red and blue, so it's a little bit more clear. And that carbon is a primary alkyl halide, so that's perfectly okay. I can then do this again. And in this case, I have a methyl halide, because this carbon is just a CH3. So great. Now I have, I don't know what that is. My carbon backbone, but my difference is I have a triple bond and then I have a trans double bond. So I can make that a trans double bond. Oh, that's not a 1. And react my sodium metal and my NH3 liquid. So that's the easiest route. There is another route, and I'm just going to go through that route quickly. Just going to open PowerPoint because I don't have any more room. And that route is equally so here, let's call this 1 and 2. So my new carbon-carbon bond in this case is between carbon 2 and 3. So I'm only forming one carbon-carbon new bond. So I can do that as well. What my alkyl halide looks like is going to be different. In this case, 3, 4, 5, and 6. So that's going to add my new carbon-carbon bond between carbon 2 and carbon 3. It's my new bond. And there's my triple bond. Now I got to get my functionality between 2 and 3, and now it's between 1 and 2. So what I can do is I can reduce that to a double bond. And then I can add HBr. But first I want to reduce it, because if I add HBr to this, if I add access, I'll have 2 bromines. That's not useful. And if I only add 1 equivalent, I'm still going to have a pi bond. Bless you. So this particular triple bond is going to reduce to a double bond. It's not going to reduce to cis or trans. So you can use either Lindlar's catalyst and your H2, or you can use your dissolving metal. Lindlar's catalyst is probably a little bit more easy to work with because, again, Na metal is pretty rough to work with sometimes. But technically you can go through either because that's neither a cis or a trans double bond. But now we have a more substituted double bond on carbon 2, and now we can do what we've been doing in all the other examples. But notice that this is taking more steps than the other route I showed. So we can add HBr to get our Markovnikov addition. Onto carbon 2. And then we can get our more substituted double bond by using our big, small strong base. I'm tired. Small strong base to get our most substituted double bond. So that route works. It is a couple of more steps. Why might you use it? Well, maybe you didn't have the other alkyl halides, but you have this alkyl halide. So this route's viable. There's nothing wrong with it. Usually we'll want the least amount of steps. What's the difference between just one more step? It's really no big. If it's the difference between 10 steps and 2 steps, clearly 2 steps is better. But this is only a difference between 3 steps and 4 steps. So both work pretty well. Any questions? Is there any from chapter 12 assignment you absolutely want me to go over? Okay. Have a good evening. Be careful going home.
Thank you.
You're welcome. Yeah.